Welcome to part 2 of chapter 8, Stoichiometry. We're going to start this video with limiting reactant, a couple of words that put fear into general chemistry students. It is a new concept, but the way in which we're going to determine these things is going to be based on our previous knowledge of stoichiometry, which is based on our previous knowledge of mole conversions. So in your Canvas course, there is a great simulation that I have put called Reactants, Products, and Leftovers. It is a PhET simulation, and it should work on your phones as well, so I highly recommend that you play with it. The game is super cute, and it, I think, helps a conceptual understanding of what a limiting reactant is. So definitely go for that simulation. Let me just write a note, simulation in Canvas is going to be helpful for your conceptual understanding of this, which is now you're really going to start to feel that crunch if you feel like you have been pretty good at the math so far, but maybe a little shaky on like what the numbers mean. With limiting reactant math, you really have to understand kind of what you're doing, not just follow through on the math. So try to slow down, make sure you're labeling lots and lots and lots of things and showing all of your work in dimensional analysis. I promise you that it will make limiting reactant problems so much easier. So what is a limiting reactant? So let's go back to our pancakes, shall we? So you remember our pancake recipe, that's like our chemical reaction. Suppose though that instead of just giving you like 8 eggs like we did in the last video, suppose I give you an amount of all 3 of my reactants. I look in the cabinet and I find I have 3 cups of flour. You check the fridge, we have 10 eggs. And then I look in the cabinet again and I find we have 4 teaspoons of baking powder. We're trying to make maximum pancakes, okay? We're like having a super Sunday brunch, max pancakeage here. So how many maximum pancakes can we make? With these bits of ingredients and with this recipe, following it exactly, I want you to pause and see if you can figure it out. Did you work it out? So, how did you do this? You probably said, well, 3 cups of flour with 1 cup of flour makes 5 pancakes. 3 times that many is going to make 15 pancakes. You might have even done that in your head. Now, if you know what I'm going to probably get at, is that you'll want to be doing this with dimensional analysis, and so maybe you set it up like that. But it probably didn't require that you do a lot of thinking. The 4 teaspoons and the 1/2 teaspoon maybe required a little bit of gymnastics with that fraction there, or you just plugged it in as 0.5 and went with that. So what's my answer? Oh, that was a blank slide. So here, starting from the right side, my 4 teaspoons of baking powder is going to yield me 40 pancakes. I use the word yield here because I want to introduce you to that word. It means the amount of product. I'll have a slide in a few that shows you just a summary of the new words we're learning in this lesson. So I can make, okay, so if you only look at baking powder and assume infinite everything else, you get real excited. We're like, ooh, we can make 40 pancakes. We're going to have the best brunch. We're going to feel so sick to our stomachs later. So 40 pancakes, I'm super excited about it. Okay, but then let's say then we look at the eggs. Well, we did some calculation with our eggs, and our eggs tell us we can make 25. So can we make 40? We can't make 40 because we have enough baking powder to make 40, but we only have enough eggs to make 25, and these things have to go together, right? Okay, so now I'm a little more bummed because 25 is not quite the fantastic pancake number that I was expecting. 40 got me really excited, so cutting it down to 25, which is probably better for our stomachs, right? Okay, but then we look at our flour. And even though it kind of looks like I've got a lot of flour, 3 cups is quite a lot of volume of flour, 3 cups only yields 15 pancakes. So I have enough baking powder to make 40. I have enough eggs to make 25, but I only have enough flour to make 15. So I can now tell you for certain that with these ingredients, my maximum number of pancakes is 15. Because once I make 15 pancakes, I run out of flour. Run out of flour after 15. And this will have to be moved so that you can see it all together. So we can't make 25. We can't make 40. We run out of flour. So unless you're gonna go to the store and buy me some more flour, these other things, I like to call these numbers my dreams. I dream of 25 pancakes. I dream of 40 pancakes. Isn't that wonderful? It's in my dreams. In another universe where the laws of conservation of matter don't apply, I could maybe do that, right? Or if I don't follow my recipe, or if I go and buy, more flour. But let's assume I can't do that, right? I ran out of flour after 15. 15 is the maximum number of pancakes I can make given these restraints, given these ingredients. So therefore, that is called my theoretical yield. It is the maximum number or maximum amount of products with these reactants. Okay, with what you're given is the most you can make. So don't come to me and tell me, ooh, we can make 25 pancakes. Get out of here. We ain't got enough flour for that. So what does that make the flour? The flour is my limiting reactant because it limits how much I can make. These other reactants are called excess reactants because what's going to happen is that once I make my 15 pancakes, I'm going to have extra eggs left over, and I'm going to have extra baking powder left over. So they're excess. We have more than we need. Okay, that's what excess means. So some new terms I'm going to summarize for you in a moment. Limiting reactant, it limits the amount of product you can make. It makes the smallest amount of product. So makes the smallest amount of product, which just so happens to be the theoretical yield, which is the maximum amount you can make given these reactants. So the smallest option is the maximum option you can make. And I'm going to talk about maximum here to compare maximum with what we actually make. So here's the deal. On paper, I can make 15 pancakes, but I have to actually make those pancakes. So what happens if I burn 3 pancakes and one of them falls on the floor because I was trying to do a flippy thing? Then I have another number of pancakes, which is my actual yield, aka experimental yield. Which is the real amount of product that I really actually made. So taking this back to chemistry, I calculate my theoretical yield and my limiting reactant. Okay, these come from calculations, and I dream of these 15 pancakes. If I'm perfect at making pancakes, okay, 15 is my reasonable number I can make if I'm perfect at making pancakes. But turns out I'm not perfect at making pancakes. So 11 pancakes is how many I put on the plate for us to eat. So that gives me my last term, which is percent yield. So the percent yield, so our percent yield, sorry for that break, is I guess a measure of how well we ran the reaction. Did we make the maximum amount that we could make with these ingredients? So it is going to be your actual, or remember, experimental yield divided by your theoretical yield times 100. So in my pancake scenario, I'm only 73% effective at making pancakes. If I worked at IHOP, I would probably not have a job if I spilled or burned this many pancakes, right? So ideally, you want your yield to be close to 100. Theoretically, your yield could not be more than 100 because how can you make more than what you could make in a perfect scenario. But sometimes we have contaminants in our experimental yield, mostly like water that we didn't um, heat off as much as we needed, or something dropped in there, a hair got in there, or something in our lab where we could have more than 100% yield, but it means there's something contaminating our sample. If I get less than a percent yield, it's because exactly the reasons why I got less than percent yield here. I lost some of my sample. I lost some of my product. I was pouring it out of a beaker and some of it splashed out, or I was heating it up and some of it splattered out of the heating vessel. So there's lots of reasons why you wouldn't have 100% yield, and you need to be good at thinking about those things by looking at procedures and finding places where I could lose product, or finding places where contaminants might remain in my reaction container. So as a summary of these terms, this is just a quick slide on the new terminology that we've talked about. So of course we're going to put it to practice. So I'm giving you some hints here to kind of get you started, reminding you of maybe a mole ratio that needs to be used. But this is how you'll see these problems. You will see a chemical reaction, or I'll have you write a chemical reaction, and notice that I'm giving you information about two reactants. So that is always indicative of I need to find a limiting reactant. So I'm specifically asking you here to find the limiting reactant and the theoretical yield, but it won't always be find limiting reactant first, because in order to find the theoretical yield, you also, by default, have to find the limiting reactant, just like we did with the 15 pancakes and the flour. So pause and see if you can work this out, if you can figure out the limiting reactant and the theoretical yield. So here's what this is going to look like. I want you to separate and analyze. So just like we did with the pancakes, we looked at each reactant separately and decided, okay, how many pancakes can I make with eggs? How many pancakes can I make with flour? Here, we're going, how much products are, let me just write this up here, TiCl4, titanium 4 chloride. How much product can I make with this reactant? How much product can I make with this reactant? We separated them. I didn't add them together. I didn't divide them. I didn't take an average. I didn't subtract them. I just separately analyzed them. This is the easiest, most straightforward way of finding limiting reactant and theoretical yield at the same time. There are other ways to find limiting reactant, and you may find those other ways if you're utilizing YouTube for some help, if you go to a tutor, if you move on to your general chemistry, your instructor may show you another way. But for this class, I'm going to strongly recommend that we just stick to one, what I consider the simplest way to both find limiting reactant and theoretical yield at the same time, which is take your reactant, find the amount of product you can make with each reactant separately. The smaller amount of product is your theoretical yield, and the reactant that gave you that, so back it on up, is your limiting reactant, which means that the other reactant is your excess reactant. So now try with mass. Find my theoretical yield in grams. So go ahead and pause and work that out. So add some places to work here. I'm not going to go through all of the tiny little pieces of how to organize this as far as your conversions and stuff, because y'all need to be able to do that at this point. So text me if you want me to look over your work. But so I need to remember, if I have two given amounts of reactants, I have to separate and analyze. So we're going to focus on the theoretical yield, and in doing so, find the limiting reactant. So I'm just going to show you the work. If you have questions about where I'm getting numbers, how I know to use these conversions, please screenshot this right now, text me and ask those questions. Pretend like this is a real-time class and you can ask these questions. And I just went to the wrong thing. So I'm trying to find the amount of NaCl because that's my only product. Sometimes you'll have more than one product. Just make sure you're using the same product for both reactants and you'll be good to go. And then my second line of work, because I've separated and I'm analyzing my reactants separately, don't forget the molar mass for diatomic is different than the molar mass for just a single atom of chlorine. My molar mass comes from my balanced chemical reaction, and the coefficients are the big numbers in front of my compounds in the balanced chemical reaction. If you are confused about any part of this work, text me a screenshot of it and I can explain what I'm doing. So let's see. I get 135.14. Let me make sure that's correct because I talked while I was typing. That's not right. Okay, hold on. 53.2 times 2.99 times 58.44. 35.23. I got three different things. Okay. All right. 65.8 divided by 70.9 times 2 times 58.44 is 108.47 grams of NaCl. I can't add these. I can't divide them. I can't subtract them. One of them is my theoretical yield and the other is my dreams. The smaller is my theoretical yield. And the other is my dreams. I can dream about 135 grams, but after I make 108.47 grams, I run out of chlorine, and I can't make sodium chloride without chlorine. So let's go ahead and just clean it up and give me some sig figs for my final answer. I need 3 sig figs, so I will say 108 grams of sodium chloride as my final answer. And I need one more part to my answer, which is what is my limiting reactant? My limiting reactant is chlorine because it produced the smallest amount of my product. So hopefully that makes sense. If not, please send me a text or email. So, okay, let's take this practice because we just found the theoretical yield. So look, our theoretical yield was, what was it? TY for theoretical yield, that's 108. I got 108 grams of sodium chloride as my theoretical yield. Let's say I go run in the lab, okay? And I do this reaction and I get actually 86.4 grams. Find my percent yield. Okay, my percent yield is gonna be, go ahead and write this out what it is because it's gonna help me. Actual yield or experimental yield over theoretical yield. So whatever term that you're using is fine, actual or experimental, times 100. What's my actual yield? 86.4 grams of sodium chloride. And guess what? The substance in the unit has to be the same if you want it to cancel to give you a percent that doesn't have a unit or a substance besides a percent sign. So we have to make sure that that cancels out. So I have 86.4 divided by 108 times 100. That is going to be 80, but I need 3 sig figs, 80.0% to give myself 3 sig figs. I'm 80% effective at running this reaction, which may be good depending on how hard the procedures are, right? Okay, so let's do one more. So give me the theoretical yield here. Sorry, let's do it in grams. And then I'm giving you an actual yield here, so you can find You can also find percent yield. It's not typed in, but you can find percent yield as well. So how about that? How about we just, let's change it. Let's change it up. Let's change it up. Let's find the percent yield of copper. So now you can pause. Let's find the percent yield of copper. Let's rework this a little bit. So in order to find the percent yield, what do I need? So start from the end. If you're not really sure where to start, I need my actual yield over my theoretical yield times 100. I always have to give you actual because you can't go in the lab and run the experiment and then come back and finish working on this, right? So the actual yield here is 87.4 grams. We're not going to use that in any other math. You're just going to set it aside on a little shelf and say, okay, I have actual yield. Here it is. That's my actual yield. Okay, I'm just going to set it aside. So what do I need to find? I need to find theoretical yield. If I'm given amounts of 2 reactants, in order to find theoretical yield, I have to separate and analyze, therefore finding my limiting reactant in the meantime. And again, I'm not going to go through all of your conversions and your given and your unknown. I'm going to separate and analyze. And I'm just going to give you some answers. And you can please let me know if you, I don't want to give too much away. I want you to really to be able to analyze your own work. But let me know if you have questions, you want me to look over your work. I can absolutely do that. Okay, here's what we get. Which one is my theoretical yield? The smaller of the two. So I'm going to bring my actual yield into it over my theoretical yield based on my formula for percent yield. That means that my copper 1 oxide, make sure you know why I said copper 1 and not copper 2, is my limiting reactant. Don't tell me this is limiting reactant because that's a product. It's not the reactant, so it can't be limiting reactant. So if you have questions right now and you're like, what about this? Or I did not get these numbers. What is she doing? Pause. Ask me for help. Text me. My final answer is 85.9% yield of my copper.